record manually right now for today. That's a lot to ask of a guy like me. Remember that every single day? There's no way I can do that. That's impossible. Got to get it on automatic. I will figure it out. Things you should have told. All right. So, in my opinion, well, this is not my opinion. This is just true. Yesterday, we spent 2 days on 3.7 because it's pretty important to understand the chain rule, and it's no joke to understand it. For a couple reasons. One of them is because it's kind of a challenging rule, but secondly, it's now encompassing the other three, and so you should have noticed in your assignment that you had kind of all four rules coming at you now. It's like I liken it to juggling a lot. When I first showed you the power rule, we discovered the power rule. You're like, power rule? Yeah, I don't have to do this long form anymore. You're juggling one ball. That's pretty easy. I can do this. I'm all excited. But you should notice in your assignment last night, you're now juggling four balls, and it's kind of not hard to suddenly have questions that you didn't even think you had before. Some of which were asked me, and let me just highlight one of them now. Somebody said, like, what if you're sitting there with e to the 4x and you're trying to find the derivative of it? Well, isn't it just power rule? Like the 4x comes down front, and then you take the exponent and subtract 1 from it. Like, all of a sudden, because we dealt with these kind of one at a time, is that the derivative of that? And of course I could just say to you, no, but like, why not? Like, how come the derivative of e to the 4x is so weird? And then we said, well, what about the derivative of, I don't know, like x to the 4th? Well, we said, yeah, power rule. The 4 comes down front. Now that's x to the 3rd. It's kind of like, yes, no.
But e is different.
Yeah. And so at its very base, I want you to notice, if you clear away the wreckage, like, don't forget e is just a number. Like, e is 2.7. It's a decimal that keeps on going, and so we give a name to it. But the reality is these two problems are more like, one of them is like 2 to the 4x, and the other one is like x to the 4th. Like, this is, well, a power equation. I mean, like, the x is in the base, and the exponent is a number. And so they behave a certain way, and those behave, well, like the power rule. And so they're called power equations. That's why it's called the power rule. So when there's a number up there, 4 or even 4/3 or 1.6, like when there's a number in the exponent, that's the power rule. But when you've got a letter in the exponent and a number is down in the base, remember, those are exponential equations, and they're different. Remember logarithms? Like, in order to solve exponential equations, you have to get logarithms involved. Like, they're a different animal, and they're different in terms of derivatives too. And so, when you take the derivative of e to the 4x, then you sort of need to think, oh yeah, these exponential equations are really different. The derivative of e to the junk is always just e to the junk. That's really weird. But then, because of yesterday, you say, well, that's not just e to the x now, it's e to something a little more complicated. Even the 4x is its own function. So because of the chain rule, you say, oh yeah, now you got to move on and say the derivative of e to the junk is e to the junk times the derivative of the junk. And since the derivative of 4x is 4, like, that's the correct derivative for e to the x. And so, yeah, there's two different things here. But can you see how, when they all of a sudden, when all of a sudden e shows up as a part of another problem, all of a sudden you realize, wow, I have questions I didn't have before. I thought I understood this, but now it's like, uh-oh, the balls are all starting to fall on the ground. All I'm saying is, and I say this a lot, but I'm not getting as many questions as I'd like, but like, permission granted to ask questions about stuff that we did a while ago, because suddenly you realize you don't get it as well as you thought you did. You're now in a place where, in a sense, there's nothing new for me to teach you, but you're putting it all together now, and this is not easy. And I'm going to show you something new today, but it's not really new, and it's gonna kind of blow the door open on kind of how this all works. And but like, please ask those questions. So to that end, like, as you suffered with, I hope you did the 3.7 chain roll assignment last night so that you have questions today, because you probably did not just go through that without any questions. If you did, good for you, both because of your strength of mind and also because of your maybe your attention to detail, and because you actually really understood all those previous rules. And so maybe you were able to juggle a fourth ball when I handed it to you. Good for you. But it would not be weird for you to say, you know, I actually have some questions. So before I show you yet something else, anything happened last night that you want to talk about?
I did. I ended up solving it last night, but I just found it weird. Question number 17, it uses a table and you have to find the derivative of the table, but not solving the function. It was very, like, I eventually solved it, but could you maybe talk about that a little bit so just I fully understand it?
Yeah, that's an example of like a question a mathematician makes up just because it's weird. I actually was looking at that and thinking, one of the funny things that happened with this class is I made the original class and I picked all the problems that I liked, and then we had another teacher look at it and kind of add some problems to it. That's probably one that I wouldn't have stuck in there personally, but I actually did look at it before you guys did it, and I decided I think I will leave that in there. Yeah, that's kind of a weird question if you haven't gotten to it yet. So I think I will pull it up real quick. And I purposely kept 2 days for 3.7 and 2 days for what we're going to talk about today to try to give a little bit more what I like to call soak time. Like, you just got to soak in this a little bit to make some sense of it, and you need time to do that. So the question that Eve is referring to, if you haven't done it yet, is the last one. Is it the last one? I have a memory it's the last one. You've said 17, but maybe that's the last one.
Yeah, it is the last one.
Yeah, this is a weird question. Can you see that okay? Basically what it's asking is, like, I just want to help you interpret like what the knucklehead who made this problem up was thinking. So it's like, let's find h prime of 4. And notice what they're doing is they're not giving me an equation. They're actually trying to make this easier on me, but it's just weird. It's a weird question. Find h prime of 4. Okay, well, I look up here in the chart, which is kind of a list of ordered pairs, and I don't see an h prime. Great. Okay, well, then it goes on and says, oh, by the way, h prime is, or h, I don't know what h prime is, but h is one function times another function, f of g, or f of x times g of x. It's like two functions multiplied together. And so what they're trying to get at is, oh, I got two functions multiplied together. Well, I don't need h, I need h prime, so I got to take the derivative. How do you take the derivative of two functions multiplied together? What's the rule that governs that?
Product.
Yeah, product. And so notice the next question is divided, so that's quotient, and then it's function inside of a function, so that's chain. And they're trying to keep you from actually having to take a derivative, but it's like, do you see product rule? So, okay, product rule. Okay, so I have to take the derivative of f prime, the derivative of f, which is f prime, times g left alone, plus the derivative of g, which is g prime, times f left alone. And then evaluate those at 4. Well, notice I have all those up here, evaluated at x is 4. So one thing that's weird about this is every single time they said what's happening at 4, I only need this column. I could like erase these 3 columns because this is x is 1 and x is 2 and x is 3. So the ingredients for this would call for f prime of 4. Well, what's f prime of 4? Well, x is 4. There it is. It's 1. F prime of 4 is 1. What's g of 4? G of 4 is, well, 2. What's f prime of 4? Well, that's 1. And what's g prime of 4? Well, that's also 1. So, the product rule is multiplying expressions together and adding them. And so they're trying to just give you practice in like, what does it look like to do all these at the same time? But that's kind of a weird question.
I was more talking about the third one where you're supposed to use the chain rule, but there's no exponent. So how would you do that one?
Yeah. So what's the derivative of f of g of x? That's f of junk. Well, the derivative of f of junk is f prime of junk. So that'd be f prime of g of x times the derivative of g of x. So let's go back to the other screen now. I'd actually be really curious to know what the person who made this problem up with their mind was. Like, are they thinking they're helping me think this through? In a sense, they are, but so you're sitting here with f of g of x, and you're saying, let's take the derivative of that. Okay, well, the definition of the chain rule is the outer function, you take its derivative. What do you do with the inner function? Nothing, you leave it alone. And then you say times the derivative of the inner function.
Okay, I got it.
So then if you say, okay, well, cool, those are 4s now, and just for everybody else's sake, Eve put some thought into this. So she's like, okay, I'm done, I got it. But for the sake of everybody else, this is saying, well, now go evaluate what g of 4 is. Well, the chart might tell you that's 3. So now you're sitting there with f prime of 3. And the chart tells you what g prime of 4 is. Maybe that's 7. And now this says, what's f prime of 3? Well, the chart tells you f prime of 3 is like 4. And so now, oh, okay, it's 4 times 7. And so the answer is 28. They're just trying to get me to practice the concept of how to evaluate this, except for they're trying to save me the trouble of having to actually do it with some complicated equation. But it might be harder than actually doing it with a regular equation, I think. But anyway, I think that's questions worth discussing. So good question. What else?
I had a question on I had a question on 10. I got the answer half right, but for some reason my um the end piece was like -1 over x plus 5 squared when I got -1 over x plus 5 to the 8th. So I
Yeah, and
was
that was like a fraction sort of a question. It was like, I'm just looking back, it was something like this, like x plus 7 over x minus 2, except for all of that was raised to some nasty power like 9 or something like that, right? Just to make
yeah.
sure I'm okay. So then what you should see is temporarily, to get chain rule understood, you should see just this whole thing is, yeah, whatever, junk to the 9th. You can't see this right now, can you? So you got to see this as like junk to the 9th. Okay, well, deal with junk to the 9th. If I deal with that, the 9 would come down front, the junk inside stays unchanged, and this goes down to the 8th. Junk doesn't change, so I'll write the junk in there. But now I've got to multiply by the derivative of the junk, right? Oh, well, that's not simple. Like that junk is complicated. Like that junk is, well, the quotient rule. So I find myself thinking, God, I'm going to lose track of what's going on here. So let's go over here and like figure out what junk prime is. In other words, what is x plus 7 over x minus 2? What's the derivative of that? Like just to finish the chain rule, it's like it's asking me for the quotient rule. So it's like, man, I could get lost here really easy. So, okay, well, what's the derivative of that based on the quotient rule? The quotient rule says derivative of the top, which is mercifully just 1. I'm sure glad that wasn't x squared plus 7x minus 2. The derivative of the top times the bottom left alone minus the derivative of the bottom, x minus 2, the derivative of that is just 1. So minus the derivative of the bottom times the top left alone all divided by the bottom squared.
I see where I went wrong now. Thank you.
Yeah. So then I can say, okay, clean this up a little bit and, replace this up here. It's really hard to keep straight. I had somebody in the chat ask me about, there's like an ugly sign question too. Let's just do something like that really quick. Like, what if you're sitting here with, say, the sine of x, but then it's multiplied by the cosine of e to the x minus 2 or something. Let's make it x squared minus 2. So you're trying to take the derivative of that. Again, what you got to see is, I see some chain rule over here because it's cosine of junk. Like, it's not just cosine of x. Notice I don't see chain rule there because it's just cosine of x. It's not cosine of junk. It's cosine of simple x. So I'm seeing chain rule over there.
And you see power rule, right? Because you're doing stuff times stuff.
And then I see like that is squared, so I see power rule, but then I also see product rule. The product rule right there. So it's like, gosh, man, this is confusing. Again, which one of those dictates what I do? Should I be thinking chain rule? Should I be thinking power rule? Should I be thinking product rule? There's an right answer to this. If you don't get this, you don't get this right.
Shouldn't you be thinking product rule? Because that's the main function. Not the main function, but that's the main part of the derivative. And as you solve that, the rest will solve itself because you have to take the derivative of certain stuff.
Yeah, the key is they're all going to come up. Like, you're going to do all of those. You're going to do the power rule because of the x squared. You're going to do the chain rule because it's cosine of ugly. And you're going to do the product rule. But which one governs it? Which one is the one that kicks it all off, inside of which you'll do all the other ones? And the answer is product rule. But why? Like, do you just feel that? Do you just see it? You feeling it? The technical answer to this is because in the order of operations, this would be the very last thing you would do. Like, if I said, hey, evaluate that when x is 6, the very last thing you would do is that multiplication. Therefore, that's the outer function. That's why I keep using the illustration of a present. In other words, that right there is the bow on the present. That's the very last thing you put on the present when you got all done and gave it to somebody. And then when they open it, they got to open it by opening, well, the bow first. They got to undo what you just did. So they're going to do the outer stuff last. That's the very last operation, is that multiplication. So you should be thinking product rule. To keep yourself from screwing this up until you get better at it, maybe you don't even do anything. Just say you're going to do it and then do it later. What do I mean? I mean, if this is my u and then this whole disaster over here is my v, then doesn't the product rule say u prime v plus u v prime? So, okay, u prime. Well, maybe you're smart enough to say the derivative of sine is cosine, but maybe just so you don't get lost, you say, I'm going to take the derivative of that times v left alone. Thank God I get to leave that alone. That's a disaster, you say. Plus u left alone, the sine of x left alone, times the derivative of v. Oh no, I got to take the derivative of that. Well, don't try to do it too soon. Just write down that you're going to do it. And again, I'm only saying this if this is confusing. So there's my u prime, there's my v, there's my u, there's my v prime, but I haven't done anything yet. Now go do it. Okay, well, u prime, super easy. Thank God. It's not the sine of junk, it's just the sine of x. So the derivative of that is cosine of x. Rewriting this because I didn't have to do anything to it. Rewriting the sine of x. But now it gets ugly because what is the derivative of cosine of junk? This is chain rule. You're doing chain rule as a part of this. The derivative of cosine of junk is negative sine of junk. The junk is unchanged. What does this person, like, why does this look wrong? Some of you are making these kind of algebra mistakes. What I said was true.
It's because you're timesing the sine x times the sine times the junk, but what it looks like is you're doing sine x minus the sine of junk.
Yeah, you might understand what you're doing, but you should write, it's u v prime, so it's multiplied. And so, at least write a multiplication sign, probably even better to write a parenthesis around that whole thing. So the derivative of cosine of junk is negative sine of junk. But again, this is junk. It's still a mess. What does the chain rule say you still have to do?
Multiply by the derivative of the junk.
Derivative of the junk. But even that is a mess, because what is the derivative of e to the x squared minus 2? Well, even that is a chain rule. This is like a chain rule inside of a chain rule. The derivative of e to the, like, I'm just writing this down below because junk prime is even not simple. Derivative of e to the x squared. Well, the derivative of e to anything is e to anything, we said. But even that you're not done, because that's e to the junk. The derivative of e to the junk is e to the junk times the derivative of the junk. There we go. So all of that has to get multiplied on the end of this. Like, no wonder this is hard. And then maybe I can clean that up or write it a little differently, whatever. I don't want to go into that, but this is not easy. That's my point. You should have questions. All right. So we have plenty of time to talk about this. Let's wade into it. 3.8 is actually going to help you. And let me show you why. Implicit differentiation. Oh my God, I think I spelled that right. My work here is done. I spelled differentiation correctly. Now, my friends, as I hinted yesterday, we enter Narnia. We go through the wardrobe into a different world. And it turns out this world has been around us all the time, and you just haven't noticed it. So in a sense, I want to say you already know this. So, you know, if you're sort of panicking, like, oh my God, you're teaching us something new, I'm not ready. You already know this, and it's going to save you some trouble. So let's say you're sitting here with this equation, y equals 2x cubed plus 7x minus 5, or something like that. We've been taking the derivative of that, right? And we've been saying, okay, cool, this is really easy. Like, remember these days? This was great, right? Power rule, woo, yeah, baby. Power rule, y prime equals 6x squared plus 7. Yeah, I got this, man. I volunteered for that one. Correct, that's right. But I'd like you to think about this on a little bit larger level, in the sense that with algebra, haven't we said with respect to equations like this, that I can do the same thing I want to both sides? Like, could I square both sides? Yes. Could I add 19 to both sides? Yes. Could I take the natural log of both sides? Yes. Could I multiply both sides by 17? Yes. I can do anything I want to both sides. Well, I'd like you to understand today is this is what we need to do. We need to take the derivative of both sides. And we've been doing this all along, but you just haven't noticed it.
Is this what you meant by the prime? Y prime the other day?
Yes. So would you agree that the derivative of x is just 1? But what's the derivative of y? Well, isn't it also just 1 then? Like, x is a letter? And the answer is no, it's not. Why not?
Isn't it because the whole function is y?
It's because y is so complicated. Like, look right up here. Look what y is. Y is really ugly. What you need to understand is there's one more part of the statement. Take the derivative of both sides with respect to x. This statement right here is really important. In other words, we've been taking the derivative with respect to x the whole time. Keep in mind, derivative means change. And so if I'm in my garden, I might decide, I don't even go in my garden, I don't want to keep using this illustration. If I decided I wanted my tomato to grow better, I might decide to change how much fertilizer I put on it, and then I would look to see did the tomato grow better, right? But could you do it the other way around? Or could you change other things? Like I'm gonna put a grow light on it. I'm gonna add more water. Like there's all kinds of things you might change. And so the idea is, if you said, I want my tomato to grow better, what can I do? I can put a grow light on it. I can add fertilizer. I can add water. I got 3 choices of things I could change. And I'm hoping that would result in a change in my tomato growing better, tasting better, whatever it is I'm trying to do, right? There's all kinds of variables there. You have G for growth, you have F for fertilizer, you have W for water, and you have L for light. Those are all variables in the tomato growing equation, if you will. And I could change any of those and see how it's changing something else. And so if you were to try to get your tomato to grow better, you would not want to change the light, the fertilizer, and the water all at the same time, because if it did grow better, you wouldn't know which one did it. So you'd want to say, I'd like to see how the tomato grows with respect to fertilizer, like D growth, D fertilizer. Does that make sense? I want to see how it grows if I change just the fertilizer. Because the end result is, if I realize that water didn't make any change, then fine, that's not the problem. I mean, what's really important? What actually makes it grow better? There's all kinds of variables. And so what I'm talking about is the big picture. The entire time, what we've been doing is finding dy dx, not dx dy, although that would be perfectly fine to find. We're looking for this thing. We've been looking for this thing the whole time. We've been looking to see how x changes. The derivative of y then is actually not y, not 1, but, well, y prime, like it's the derivative of y. We don't know what it is. Notice up here how complicated y is. Of course, the derivative of it is with respect to x isn't 1, because look what y is equal to. It's really complicated. The point is we've been taking the derivative of both sides the whole time. So we look at that blue equation and we say, okay, what's the derivative of y? When we write y prime. You just haven't noticed you've been doing that. You never said it was 1, right? Like you did with x. And that's because you're taking the derivative with respect to x. Or you might even rewrite it as, what's the derivative of y? It's the derivative of y with respect to x. That's a better notation. So the left side, we've been doing this the whole time. And then we go to the right side and we say, hey, look, a bunch of x's, cool. Well, since I'm taking the derivative with respect to x, then I can actually take those derivatives. And as we said, then you get 6x squared plus 7. And so awesome, good job. Like we've been taking the derivative both sides the whole time. You just haven't noticed it. So part of you should be saying, who cares? Like what good does that do? Well, let's go into Narnia. There's a whole class of equations that you don't know exist. I mean, I hinted at this a little bit yesterday, but if you look at your graphing calculator, I won't take the time to turn this on, but if you go to the y equals screen, you get y equals. Like that's the only equations you can type in. You can only type what mathematicians call explicit equations, not implicit, explicit. They're explicitly solved for y. But you can't graph stuff that isn't solved for y. Well, you can in Desmos. Let's do it. Enter Narnia. So I'm going to make up an equation right now, just totally from scratch. And what it's going to be is just an equal sign with just a crazy collection of x's and y's. And I'm genuinely making this up. Perhaps you can tell that I'm doing this. Maybe I'll get lucky and there'll be something really cool. Maybe it'll just be really stupid. I don't know. I probably made up the coolest one I've ever made up for 8 o'clock class. So maybe yours will be terrible because my creative juices are gone. It was really amazing. It was like a lightning bolt that was curved. It was amazing. I'm going to be famous as a result of that. Let's see. Let's take x, but then let's multiply it by y, and let's even square y. That would be fun. And I don't know. Let's add that to, I don't know, the sine of y. And let's see. Let's subtract an x squared. Let's even throw a y in there. How come I'm not getting a graph? Where's the graph? How come I have no graph?
You need an equal sign.
Wish I could improve on that. You can't have a graph if you don't have an equal sign. So let's go to the equal sign. Now, I could just say equals 2, x equals 5, or I could just keep going. Like I'm having a great time here. So let's make it, I don't know, 5x. And yeah, every term's got a y in it, so let's not have that. Was it squared? Should I square it? Oh, there we go. That's pretty fun. It's not near as cool as the one I made at last class. But that's a crazy looking graph. Now you've never seen a graph like this. And again, I've kind of said this before, but there's a good chance that no human being has ever seen this graph. You understand that? Like I'm making something up from scratch here, and there's a good chance that no human has ever seen this. Desmos only existed as a tool that would graph implicit functions, implicitly defined. And that's just code for you can't solve this for X or Y very easy. Can you see that this would be really hard to solve for X or Y? You can solve it for X using the quadratic formula, but you can't solve it for Y because there's Y's, Y squareds, and the sine of Y. You couldn't even solve this for Y, it's impossible. And so we weren't able to graph this stuff. I actually don't understand the code as to how some nerd figured out a way to graph this. But no human being has probably ever seen this before. I mean, it's really kind of just cool to think about. So we're in Narnia in the sense, we're in a world of equations that we didn't even know existed before, and yet they were around us all the time. We just didn't have the technology to see it. So now I'm going to do one more thing that's really cool. Instead of just limiting it to this, I'm going to go back in there and actually put coefficients in front of all these. Notice I had ones in front of them, kind of without thinking about it. I had ones in front of all of them. So now I'm going to go back and throw the door open to more possibilities. And so I did pick a 5 for that one, but I'm even going to take that away. And so now I have, well, they're all ones right now. Notice when I made sliders for them, every one of them is 1. And so let's see what happens if I make A something else. Let's see what this looks like. And what I want you to understand is we're looking at like a whole class of functions now. It's like a class of functions, and all I'm doing is messing with this coefficient. Isn't that cool? Like, look at it. It goes over there and boom, pops together. And all of a sudden I have this weird looking eggs being born out of the ground. But all of a sudden I want to name this and be famous for the crazy name. Notice, by the way, what caused that is A was 0, which means it took away the xy squared term entirely. It took it out. And so I get this really cool graph. And so let's see, what does B do? Isn't that cool? It's like it almost looks like life, like if you studied science, mitosis, cells dividing, which turned into you. It looks like cells are dividing and turning into something else. Just crazy cool graphs. So
I have a question. Does this apply to our project upcoming? Because you said today's like work would apply to the project. So the project says finding the tangent line on this. So do we have to solve the equation, find the tangent line, and then make a slider out of it so it moves around our graph?
yes, that's exactly what you have to do. And I have a whole day devoted to it so that we can kind of work together a little bit on it. But the concept is basically this, like, wow, here's a whole class of equations that is just so much more interesting than the boring parabola. Now, the parabolas are cool. They're the reason that you have a television signal at your house. They do an amazing job. That's a really cool graph. But what a simple graph compared to this. This is an amazing graph. And so, of course, mathematicians say, well, is there a way to find the slope of this graph? Can I still find the slope of it? You know, even if it's just interesting, even if there's not a purpose to it. Again, we're looking at an equation here that no one human has ever seen before. Even if they had graphed what I said before, they've never stuck these coefficients in here. So you are the first people. I never saw this before either. We're the first humans that have ever seen this graph. I mean, that's just kind of cool in a way. And so, you know, mathematicians would just say, wow, can we find the slope of this graph? Obviously, this seems really hard. Like there's a lot of slopes going every which direction here, and there's points going everywhere, and I haven't even zoomed out to see what's the pattern big term on this. Find myself wanting to play some more. Kind of like it when there's no xy squared term in it.
I'm kind of confused on how we could find the derivative on like when there's 2 points on like x equals 5 or something. I don't know how.
Everybody understand Martin's question? Because he just asked, like, how do you find the slope when x is 5? Do you notice there's 2 different answers to that? There's 2 places on this graph where x is 5, and notice x is a 0 is even worse. Look how many places you're at x is 0.
Yeah, technically this isn't like a function, is it?
Yeah, and that's why mathematicians have things called a function. See, y here is not a function of x. Y apparently depends on something a lot more than x, because when x is 5, you can't determine what y is. There's 2 different answers. So mathematicians say this is not a function. Now, it doesn't mean it's not a graph. It's still a relationship. It's still a really cool graph, but it's going to not be enough now to say what's f prime of 5, because there's 2 different answers to that. And so very insightful question, Martin. Like, but there is a slope there, right? If I tell you which one of the 2 points when x is 5 we go to, one of them has one slope that's a low negative number, and the upper one has a steeper positive number slope. And so it's not like there still isn't a slope, right? But you know, the question could be like, can you find it? And the answer could be no, but it isn't no, it's yes, which is why there's the chapter in your book.
What?
So yeah, soak time. Like, this is just amazing. Like, we're in a new world here. I mean, isn't this crazy? And yet you don't really have to learn anything new to be able to do this. Although
So
it would seem like you would.
we could pick an equation for a project and have it be impossible.
Kind of. We'll talk about that later. The hardest part of this is not finding the slope. The slope is actually really easy. The hard part is trying to find a point on the graph. Like, look at that horrible equation I just made up there. Somehow we're supposed to find an x, y point that works in that. Like, that's hard. That's the algebra, but that's harder than anything. So you do have to be a little careful. Like, you can't go crazy. But part of this project is just like play around in this world a little bit. This is amazing. I mean, the fact that we have a tool in Desmos that allows us to visualize this, that's unbelievable. So let me go back and just humanize this a little bit. I'm going to put some numbers into this. Maybe this will end up boring, I don't know, but let me just throw numbers into this, because we'll get back to this. We'll take the derivative of this before we're done. But this is pretty hard, so 2 minus signs. So notice there was a whole nother side to this graph. Like, there's a whole side over there that I didn't notice before. Notice if you zoom way out from a distance, it actually looks like a horizontal line on the x-axis, a vertical line on the y-axis, and then like a diagonal line. I mean, it's kind of weird. And it's only if you get closer that, just like getting closer to the earth, you realize there's some detail here that you didn't see before. So maybe that's only a chunk of the graph. So, you know, like, how would you take the derivative of something like that? Well, let's back up a little bit and start with something a little easier. So again, let me make something up, and maybe this won't be as interesting. Now I'm going to keep sine out of it, but I'll make it a little bit interesting. But let's consider, I love that word for some reason, consider this function. We'll kind of make it similar to that one, like it has an x and a y squared, and let's throw a 2 in front of it, and I don't know, minus 6x, and let's have a plus 3x squared, and let's go to the equal sign, go on the other side now, and let's see, an xy. Let's get an xy in there. How about like a 4xy? And are we done having fun? How about just a y term all by itself, like minus 3y squared? And I don't know, let's throw an 8 on the end of it. So, okay, there's a random function. We'll graph that in a minute and see if that's kind of interesting. But let's see if we can take the derivative of both sides right now. And would you agree we are extremely happy about all these plus and minus signs, right? Because we can do all those separately. We like plus and minus signs. We do not like multiplication signs, right? Because what does that mean I'm going to have to do to take the derivative of that first term?
Product rule.
Product rule. And then here's another product rule, right? So we don't like those. But we like plus and minus signs. And so this is what I mean when I say you don't actually need to learn anything new here. Let's see if we can wade through this and take the derivative of this. Remember what we mean when we say we're going to take the derivative. We're going to find change of y over change of x. And don't forget, it was y over x. Remember that was actually rise over run? Like that's why we have the y on the top and the x on the bottom, because we're after the rise over the run. And we defined it as rise over run, not run over rise. Put more simply, we're actually looking for y prime. Well, let's go get this. So I'm going to put the multiplication sign right there. And so product rule says, I'm going to write this up here, product rule says the derivative of 2x, which is 2, times y squared left alone, plus the 2x left alone. And now we got to think a little bit. What's the derivative of y squared? Think.
So we said that the derivative of y alone equals y prime. So wouldn't the derivative of y squared just be y prime squared?
Good question. What's the derivative of y squared?
Why can't we just use the power rule for that though?
Yeah, everybody's making really good points. Would you agree that it's an awful lot like, well, junk squared? Because remember, if we take the derivative of y, based on this equation right here, if we were to solve this for y, that y is equal to something really ugly, right? The derivative of y is not 1, it's y prime. It's really ugly. But from the chain rule yesterday, if you had the derivative of junk squared, and let's pretend for a second from yesterday that that junk was, well, you know, something like 2x squared plus 7x minus 5. Like, what do you do to take the derivative of junk squared according to, well, the chain rule? Doesn't the 2 come down front? What happens to the junk?
Stays the same.
Stays unchanged, right? You don't do anything to it. And then this goes down to a 1, but then the chain rule says you're not done. What do you still have to do?
Multiplied by the derivative of the junk.
Multiply by the derivative of the junk, right? So what would that mean for us? I mean, that's what y is. Y is a big bunch of junk. We just don't know what it is.
So we just y prime, or
Could you set y equal to something like z or something? So you could say yz squared or something?
Yeah, but you don't need to. If you just go back here and say, well, this is a y the whole time, well, then isn't that your answer? Y is something complicated. So the derivative of junk squared is 2 times the junk times the derivative of the junk.
Yeah, I think the whole
That's
idea is that there's nothing really holy about y.
correct. There's nothing holy about y is exactly right. It's a letter. We treat it like any other letter. The only difference with x is because we're taking the derivative of x, we can actually take that derivative. We don't have to think of it as junk. And we'll get there in just a second. Well, we're there right now. So there's that product rule. Worked out. The only hard part was what's the derivative of y squared?
2y times y prime.
So 2y times y prime. That was kind of the hard part of that product rule. Well, let's just keep going. Let's see if we can get our mind around what's happening here. So then I get to the minus 6x and I feel like, oh, thank God, something easy. What's the derivative of minus 6x?
6.
It's just 6. And again, how come it's not 6 times x prime? Well, it is 6 times x prime, but because we're taking the derivative with respect to x, the derivative of x is 1. So you can take the derivative of x because we're taking the derivative with respect to x, but you can't take the derivative of y. So basically, anytime you take the derivative of y, there better be a y prime. So I see back up here, for instance, there's a y, there's a y, there's a y. Every one of those is going to have a y prime in it as a part of the chain rule. Well, let's keep going. What about 3x squared? Again, that's really easy because the derivative, well, think about this in terms of y. Let's do what we just did with y a second ago. Wouldn't the derivative be the 2 comes down front, so then now I have 6. The junk x stays alone, stays the same, but then I say times the derivative of x, right? Isn't that what the chain rule says? Isn't that exactly what we just did with y? But the difference is, what is the derivative of x? You can actually take the derivative of x.
6x.
The derivative of x is 1, therefore the answer to this, like Caesar said, is 6x. Because we can take the derivative of x, because we're taking the derivative with respect to x. We just can't take the derivative of y. So we just wimp out and say y prime. Here I just didn't have to stop and say x prime. I could just say it's 1. Okay. Equals, I'm thinking product rule again. So this is my u and y is my v. So the derivative of 4x is 4 times y left alone. I said times y left alone and didn't do it. Derivative of 4x is 4 times y left alone plus the 4x left alone times the derivative of y. What's the derivative of y? The derivative of y. We don't know what it is. We're just writing it down. It's not 1. The derivative of y is not 1 because we're taking it with respect to x. And this y is really complicated if you were to solve it for x. So we're just going to wimp out and say it's y prime. I don't know what it is. I'll just write down that I'm going to do it without doing it.
Why did we write y prime over here, but on the other side we wrote 2x times 2y times y prime?
We did exactly the same thing. So back here we said, this part, the second part of the product rule, we said this was our u and this was our v. So we said the second part of the product rule was leave u alone times the derivative of y squared. But because y was squared, taking its derivative was a chain rule problem. It's uglier. The derivative of junk squared has a bunch more steps to it. So there was just more to it. Here, there's just a y. So what's the derivative of y? Y prime. What's the derivative of y squared? Oh, that's chain rule. It's 2 times y times the derivative of y. And then this happens again because look at negative 3y squared. Well, that's negative. You think of that as like negative 3 times junk squared. So you first got to deal with that 2 power, which flies down front multiplying by the 3, and then the y gets left alone. The hard part of this is you're not done. Do you understand that? You're treating it like an x if you think the derivative of negative 3y squared is 6y. Because y is really messy. What does the chain rule say? It says you have to take the 2, bring it down front, and then the y is now raised to the first power, but the chain rule says times the derivative of the junk. Basically, every time you have a y, there better be a y prime when you take its derivative, because that's what chain rule says. You have to take the derivative of y, even if there's other stuff to it. I'll erase this, but what's the derivative of sine of y? The derivative of sine of junk is cosine of junk. But what does the chain rule say? Times the derivative of the junk. Does that make sense? Anytime you see a y, you got to realize it's junk, it's messy, it's ugly. Y, this equation solved for y is huge. So you can never just say the derivative of sine of y is cosine of y. So our first example, like you should be pursing your brow and like, I'm trying to get my mind around this. It'll feel better with a little bit of time. Lastly, what's the derivative of 8? Well, that's just 0. So just to give you time to soak on this, let's like rewrite what we got here. So we got 2y squared plus 2x times 2 times y prime. So at least I can go 2 times 2 is 4, but then there's an x, there's a y, and there's a y prime. And then there's a minus 6. And then there's a plus 6x, and that's the end of that side. And then there's 4y, I can't do anything with that. And then there's 4xy prime, can't do anything with that. And then there's minus 6y prime. Like that's what I have so far. I took the derivative of both sides, and that's what I have.
I have a question. Can't you
Stay off mute a little longer. I missed you, Eve.
So can't you like subtract the 4xy prime over and like get rid of some terms?
It's just an equation. So
Simplify
this is just like any other algebra equation. Anything you want to do to both sides, you can do. If you decide to multiply both sides by 19, great. If you decide to add stuff to both sides, great. Do anything you want. But don't forget, and this is really exciting, what have we been trying to find this whole time? We've been trying to find y prime. Well, isn't there a whole bunch of y primes? All I got to do is solve this equation algebraically for y prime. The important thing is there's a term with y prime, there's one, and there's one. I got 3 of them. All you got to do is get those on the same side. And you're almost done. So let's see, I'm going to take this one over to this side. And then over here on the other side, I've got a non-y prime term, and I'm going to send that over to the other side. Just do algebra, subtracting them from both sides. So you tell me if this doesn't look right then. So let's see, I have a 2y squared over here. If this is gone, then I have a -6, but then I'm going to bring that 4y to the other side by subtracting it over. So then all the non-y prime terms are on the left. On the right, I've got that 4xy prime, and I've got -6yy prime, and then I'm going to subtract this mess over, so that'll be -4xy y prime.
Isn't there like a 6x or something?
Did I blow it? What did I miss? 6x. Thank you. I lost my +6x. Thank you. Algebraically, how am I going to get it so there's only one of these when there's 3 of them? I got 3 y primes. How am I going to get it so there's only one? I can't solve for y prime if there's 3 of them. I got to have one of them.
And you divide it out.
Yeah, like this is just distributive law. Math teachers would call it factoring, but the better way to think of it is distributive law. Hey, look, they all have a y prime, so can't I undistribute? I like that way better than distributive law. Can't I just undistribute the y prime? Take it out, leaving all of the rest of the junk in there behind? Isn't that what distributive law says? Distributive law is a way better way to understand this. Nothing happens on the other side. I'm almost done. How do I solve then for y prime? How do I get rid of y? How do I get rid of all this junk over here?
Divide it.
Divide the left side by it.
Divide it. So 2y squared -6 -4y plus 6x, all divided by 4x -6y minus 4xy. You found it. There's the derivative. And I started off with a fairly hard example here. But notice the difference, and this answers Martin's question earlier, is notice the recipe to give you the slope popped out, and it actually calls for 2 ingredients. Up to now, it's always only asked for x. This asks for x and y. So does it make sense now you have a way to determine which point you're actually finding the slope at? It's not enough just to say x is 5. You also got to say the y that goes with it. So notice like that problem actually solved itself. Very insightful question that you asked, but notice this recipe, you got to know the entire ordered pair. You got to know the x and the y if you want to get the slope.
Which makes sense because there would be multiple x like slopes for different.
Exactly. So this is kind of cool. Like it's actually working. I mean, this is really amazing.
Can you imagine doing this equation in the first week and using x plus h?
Yeah. The first week, remember, to take a derivative, we had to replace x with x plus h. Like how fun would that be? Good point, Eve. Like we're a long ways out into shortcut land, don't forget. We have 4 shortcuts now: power, product, quotient, chain. And really we just used those here. I didn't teach you anything new today. We just used the chain rule. The derivative of y is y prime.
What does this thing look like if we graph it on Desmos? Are we able to do that?
Yeah. So just to give you time to soak on it, let's go back to the original problem here. And let's graph it. Maybe we'll get lucky and it'll be cool. What just happened? I don't know. So because I can't remember that, I'm gonna take a picture of it with my phone so that I can go over to Desmos. And then we're gonna actually see if this it's almost impossible to believe this really works. Like this formula is actually gonna tell us the slope of this curve. Like it, I mean, obviously it is because I'm teaching it to you, but it's like, it just feels like this can't possibly work, can it? Like there's just no way. This is just crazy. Let's see, maybe we'll need that later. So then I'll just turn it off instead of erasing it. So I'm going into photos, pulling this up. Let's see, I got 2xy squared. Again, we're probably graphing something here that no one's ever seen before. Oh my God, this is exciting. Plus 3x squared equals, now we're on the other side, 4xy. Why didn't I give you guys an easier problem to start with? I don't know. Minus 3y squared. Ooh, this is sweet. Now, something really important. I'm about to add the plus 8 at the end. What's going to happen to this graph when I add plus 8 to it? What does it do when you add something to a graph?
When you shift it up 8.
Just shifts it up. Is it going to change the slope? If that little egg looking unit goes up, does it change the slope? No, it's the same slope. It's a little more complicated than that, notice. So I'll leave you to think about that. So this is a pretty cool graph, but now we want to find the slope of it. And so we did get kind of lucky. That's kind of a fun graph. Notice it's interesting that the graph doesn't seem to, like for some reason, X can't seem to be 5, right? Why can't X be 5? That seems weird. Why would X not be able to be 5? There's no graph past apparently 4. X can't be 4, 5, 6, 7, 8, 9, 10. Like what in the world? Like why would this graph not allow that to happen? Well, you may recognize there's a bunch of squareds in there. So to solve, you'd have to use the quadratic formula. And sometimes in the quadratic formula, don't you get a square root of negative? You get a square root of a negative. So apparently if you pick an X bigger than 4, then you get a square root of a negative. I don't know, I'm just thinking out loud, but so we got to find a point, but do you notice it doesn't seem to cross? Of course it doesn't. It doesn't cross any points very accurately, does it? Like I wanted it to go through the point like, well, 2, 2. Notice it's pretty close to going through 2, 2, but it doesn't go through 2, 2. Like this is a really crazy graph. And so does it make sense my point's going to be a decimal? But let's do something kind of fun, just because we can, because we have the time to think about this. Let's do something kind of fun. I'm going to change this graph a little bit to work for us a little bit better. Let me get rid of all the disaster of notes I made on it. Let's say we did want, remember how it was really close to going through the point 2, 2? I don't want the 2, I don't want X and Y to be the same. Let's find some other point. Let's see. How about 1, 2? Would you agree it was really close to going through the point X is 1, Y is 2? I would like this to go through the point X is 1, Y is 2. Okay, well, let's go plug all that stuff in. If X is 1 and Y is 2, then this term would be 2 times 1 times 4. So isn't that 8? So this is 8 minus 6 times 1 plus 3 times 1 squared. So this side is 2 plus 3. This side is 5. You agree with that? Now the graph already told us this is not going to be equal. Do you agree with that? This is not equal because that point is not on the graph. So let's see, if I put in X is 1 and Y is 2, this is also 8. 3 times 2 squared is actually 12. So 16 minus 12 is 4. Darn. 2 things to notice. Notice they're almost equal. That's because this point almost worked. I didn't get 5 equals 19 or 15 equals 712. They're almost equal. What is a really cool fix that we could do to fix this and make it equal? Well,
You could change the +8 to +9.
exactly, like that 8 right there. And that's why I threw that constant in there in the first place before. If that 8 was not an 8, you said it was a 9, is that true? Yeah, 9, you're exactly right. If that wasn't an 8, but it was a 9, then this would be 5. And then they would be equal. Now that's a stupid idea because now we got to go do this whole problem all over again, right? Why is that not a stupid idea?
Because when you take the derivative of the number, it turns out to be 0.
Yeah, in the very next step, didn't that turn into 0 anyway? So it's like it didn't even change the derivative. Remember how we talked about the slope doesn't change when you change the number? So if that's a 9, it actually doesn't change the answer. The only thing I have to do then is go back to Desmos and change that to a 9, and all of a sudden it goes through the 0.12. Isn't that cool? Now, again, you don't need to know this. I'm just teaching you how to think here a little bit. Now, what does it look like the slope is there, though?
It looks like 0 at that point.
I agree. Do the rest of you agree? If I go to the 0.12, which now is miraculously on our graph, doesn't it look like the slope there is 0? Now, is it 0? Maybe, but it might just be close to 0. Does it make sense if we got a slope of 0.1 or something like that? We'd say, oh yeah, that looks about right. But it looks like it's around 0. Well, what I want to do is go check. Go check we have a slope, right? We have a slope equation. So let's go find, I don't know how to say this, y prime of the 0.12. Is that okay to say it that way? It's got 2 ingredients. I guess it probably is. So let's see, I'm going to write the whole thing out. So that's 2 times y squared minus 6 minus 4 times 2 plus 6. On the bottom, I've got 4 times x, which is 1, minus 6 times y, which is 2, minus 4 times x, which is 1, times y, which is 2. Let's see, what do I get? That's 8 on top, minus 6, minus 8, plus 6. Ah, interesting. What just happened?
0.
I did get 0. Notice I don't even need to figure out what's on the bottom because basically this is 0 over some number, so I don't even care what it is.
What if the bottom's 0?
Yeah, what if the bottom is 0? Let's find out. Maybe that would be a disaster. So maybe let's check and see if that's true. If the bottom was 0, then the slope would be undefined, and the graph said it was 0. So I can already tell the bottom's not going to be 0, but let's just see. 4 minus 12 minus 8. Whew, I thought it was there for a second. 4 minus 20 is negative 16. So I get 0 over negative 16. Sure enough, the slope is 0. Wow, I can't believe it, but this actually seems to be working. It's just crazy, but this actually works. As ridiculous as that is, it actually works.
You know what else is kind of crazy to me is that technically, didn't we just take the derivative of a point that wasn't even on the graph that we took the derivative of?
Yeah, isn't that weird? We took the derivative and got it of a point that wasn't even on the graph. And yeah, like that's just crazy. So the fact that we changed it to a 9 actually did move it. Remember that did move it, and it might have changed the slope as soon as it hit there. Maybe that did change it a little bit, but yeah, that's just interesting. Now, there's a part of me that says I just started with way too hard of a problem. But let me just show you kind of with our last little bit of time here. I don't know, let's just do one other quick example. Let's do something a lot simpler, like why did you torture us with something so hard to start with? Let's just make this a little simpler. Anybody know what that graph is? By chance, from your Math 111 course?
Is that a circle?
Yeah, notice it's got an x squared and a y squared. So I think, is that a circle with a quizzical tone of voice is a good way to say that. I already forgot what it was. It was 4x. Is that a circle? I think Cheyenne says. Desmos says, well, it's circle-like. It's an ellipse. So that's kind of cool. Like that would have a slope. And by the way, planets fly around the universe in the shape of an ellipse. We're flying around the sun in an ellipse right now, slightly, not near this elliptical. But the direction you're traveling at any moment in time is pointing tangent to this curve. Let's see if we can find the derivative of this little beauty. Well, you try it. Let me give you a second.
I have a question. Wouldn't it be easier just to make it y equals by
Great
isolating?
question. Great question. Wouldn't it be, could you solve this for y? The answer is yes, you could. And would that be easier? Well, I'm going to do that really quick. Let's see, 9, I'd subtract 4x squared, and then I would divide by 9, and then I'd take the square root. So you'd be taking the derivative of that. The answer is, well, maybe it'd be easier. I don't think it is. I think it's worse.
No, I don't think so either.
Because now you have junk square rooted, and so I've got a chain rule problem. But the answer to your question, Caesar, is absolutely. If you want to do that, this is not hard to solve for y, and so do it both ways. You'll get the same answer.
Yeah,
But
then we also have like quotient rule and stuff like that too.
Exactly, quotient rule was in there. This is actually, I think, easier this way. So what we're doing really now is just saying, let's take the derivative of both sides. So again, we love plus signs. The derivative of, and I want to kind of remind us, ... with respect to x. That's what we've been doing this whole time. So therefore, when I see x's, I think, oh, great, I can take those derivatives. I get 8x for that. But what's the derivative of 9y squared? It's not just 18y, because we're taking the derivative with respect to x, and y is not x. It's not 18y. Well, it is 18y, but what's missing?
The y prime.
Y prime.
Y prime.
Y prime, because of the chain rule. As I mentioned before, there's nothing wrong with doing the same thing with x. What's the derivative of 4x squared? Well, it's 8x times the derivative of x. But what's the derivative of x? It's 1, because we're taking the derivative with respect to x. It's 1. So the derivative of 9 times junk squared is 18 times junk times the derivative of the junk. That's what I wrote down, 18 times y prime. What's the derivative of 36?
0.
0. Now all I have to do is solve for y prime. Notice there's not as many of these as before. So let's see, I guess I'll leave it here and move the, I think I'll leave the y prime on this side. I'll leave this over here and subtract the 8x over to the other side. And then all I got to do is divide by 18y. So y prime is equal to negative 8x over 18y. And of course I could reduce that, I guess, to, what is that, 4/9, and I guess it reduces right there. So negative 4x almost seems like it wasn't worth it. So there's my recipe for slope. So it calls for x and for y. Let's go to the graph really quick. Is there any points this goes through that I could, did I get lucky and it goes through any points? Probably it won't. I see something interesting. Let's see, it looks like it goes through the point 2.61. Would you agree with that? Now, does it actually go through that point? I'm just saying it looks like it. Does it actually go through it? I don't know. Let's go look. I actually have no idea. Notice the answer is no. Isn't that kind of cool? Now, it's not surprising because remember the x and y were squared, which means to solve, if I pick y to be 1, then I'm going to be taking the square root of x. And does the square root of x ever come out 2.6? No, it comes out 2.618295. And so, you know, my estimate that it's like, oh yeah, looks like it goes to that point. Notice it actually doesn't. But it is pretty close. If I put 2.6 in for x and 1 in for y, I'm going to get a pretty close answer to the slope right there. But it's not easy to find a point that works here. Again, I could do what I did a minute ago, which is I could make it go through the 0.31 by changing 36 to something a little bigger. I could add something to it. I could make it go through a point if I wanted to. In the interest of time, I'm going to stop here, but it's like we found an equation for the derivative of an ellipse, the slope of an ellipse. And again, I'm just asking you to believe me, but in this case, this is really practical. If that point, that purple point on that graph represents us flying around the sun, our speed is actually pointed in physics in the direction of the tangent. There's two kinds of speed. One is how fast are you going? Think about your car. How fast are you going? But the other is what direction are you going? Like if you're turning, it also matters what direction you're going. You could be going 60 miles an hour, good for you. But if you're not going in the right direction, then you're not getting where you're going. And so there's direction and there's actually speed itself, two components of it, if you will. So that's what's kind of cool about this. So we can sort of understand our universe and how we fly around things based on this. But let's leave it at that. We found the derivative, good for us. I want to show you one other cool example, and this will be the end for today. Would you agree from yesterday, this is the terrifying question? You should be able to do that. But would you agree that's terrifying? Because it's got chain rule since there's the square root of 4x minus 3. But then there's also quotient rule because it's 2x plus 1 divided by the square root. So it's like quotient and chain. It's like you can do this right now. But would you agree this is just an algebra statement? So before I even take the derivative of this, I think I'm going to start doing some stuff to both sides. Like, couldn't I multiply both sides by the square root of 4x minus 3? Hey, cool. Don't have to do the quotient rule anymore. But I still have to do the chain rule because I have the square root of 4x minus 3. But couldn't I square both sides and get rid of that too? If I squared both sides, wouldn't I have y squared times 4x minus 3? And then this other side would be 2x plus 1 squared. There, no more square roots. But we don't like multiplication signs. We like plus signs. So why don't I actually do the multiplications that are implied here, like y squared times 4x and y squared times 3. And on the other side, 2x plus 1 squared. If you square that out, don't you get 4x squared plus 4x plus 1? Like, do you understand these are the same thing? Those are the same exact graph. But that bottom one actually looks easier to me because I don't have any quotient rules anymore. And I kind of don't have any chain rules, although I kind of do because of y squared. But again, let's just have one more example going out the door. Let me give you a second because we got 5 minutes. Can you take the derivative of that now? Maybe you say, I think I'd rather go back to this phase and leave that alone. Maybe you want to do the product rule. Like back here, this is product rule. Maybe you just want to leave it there and say, I'll do product rule right there. You can take the derivative anytime you want, but I think this last one, arguably, is the easiest. What do you get for the derivative of that? Now that it's not explicitly solved for y, it's implicit. It's still an equation, but it's an implicit equation. Just X's and Y's everywhere. As crazy as this is, we're still just finding the slope on a curve. It's just that we're in a new world of curves now that we never knew existed before. I'm going to catch up to you. Looks like we're doing the hardest thing first. I need to see 4x times y squared, because it's letter times letter, as a product rule problem. So did you get this? The derivative of this is my u and this is my v. Product rule says derivative of u, derivative of 4x is 4, times v left alone, plus the 4x left alone times the derivative of v. So this is the only hard part. This is the chain rule part. What's the derivative of junk squared? 2 times the junk times the derivative of the junk. So there's the product rule of that. Then there's a minus sign. We just did this. What's the derivative of 3y squared? Well, the 3 times junk squared, the 2 would come down the front. So then it'd be 6 times the junk times the derivative of the junk. That's chain rule. Nothing new, really. And then the other side, because there's no y's, is much easier. Because remember, we're taking the derivative with respect to x. So the derivative of 4x squared with respect to x is 8x. The derivative of 4x with respect to x is 4. The derivative of 1 is 0. So the amazing thing is we're not taking any derivatives here. Like, we're just writing down what we're going to do. But now I look at it and say, hey, weren't we looking for y prime the whole time? Weren't we trying to, if you will, find y prime? Isn't that the magic slope, dy over dx, change of y over change of x? Like, that's what y prime is. So didn't we just, if you will, magically get a bunch of y primes? Sweet, there's one right there and there's one right there. All I got to do is resolve this algebraically for y prime, and I found y prime. So the only term on the left side that doesn't have a y prime is that one. So if I just get rid of it, as well as clean up a few things like 4 times x times 2 right here, since there's 4 times x times 2 times y, I might as well multiply together what I can. What can I multiply? Well, 8, that's it. And then there's an x and there's a y and there's a y prime. And then can't really do anything with 6y y prime. And the other side is just 8x plus 4. But then if I lose that 4y squared over to the other side, and then I undistribute the y prime out of each of those, then divide that junk away, then I have an expression, a recipe, as I like to call it, for a delicious Turkish delight in Narnia. For those of you Narnia fans, I now have a recipe. Did I make any mistakes? I now have a recipe for the slope, calling for x and for y. side note, won't do anything with this, but the question is, could you take the derivative of this statement just like it was, like you would have done yesterday, and get the same exact answer as this? You might look at that and go, what? There's no way I could get the same answer as that. But remember, if this is what y is equal to, if y is equal to that mess right there, then couldn't I come down here and replace it? Everywhere I see a y, couldn't I replace that with that giant mess right there? And then my recipe would only call for an x. Since this particular equation was possible to solve explicitly for y, then I could actually change my recipe to only have an x in it. You would get the exact same answer. If you have time, if you have mind space, you might try that. Convince yourself that you can do it. But of course, that statement right there is the sum total of everything we've learned for 4 weeks straight, right? Like you have to still be able to take the derivative of this, which is brand new to you. Like you're not good at that yet. You're getting there, but you're not good at it yet. And then I just showed you a whole different way to do the same thing. And now you're going to like somehow show they're the same. That seems like a good extra credit question. I would just want you to send me a PDF of both of that worked out, like convincing yourself that it's not true. As always, if I assign extra credit, don't do it unless you get it right. Like if it doesn't work, then ask me about it, and then you'll be learning something.
Is there like a due date for the extra credits, or?
No, I forgot I even asked them. Like I didn't give the 8 o'clock question, the 8 o'clock class an extra credit. I forget I asked it. I'll just get an email from you and I'll go, oh, that's right, I gave them an extra credit problem, and then I'll grade it and send it back to you. So no, the only thing I would say is if we get to the end of this class and you have 89%, you can't go back to this and say, can I do that now? Like you got to do it in context, like do it reasonably soon. But I don't want to limit it. I mean, I want you to, if I have to help you 3 times before you finally get it, good. That's exciting. That's cool. Good for you. And that might take a week or whatever. So now I've taught you everything you need to know to do the assignment in my open math. And I haven't looked at it yet, but I've taught you the conceptual understanding of how this works. So I'm going to go look. So tomorrow I don't have to teach you anything new. Really what we need to do is just, well, soak on it. I've tried to build an extra day in to just kind of play around with this. I just want to give you some more problems. I have all kinds of other cool equations that I've made up over the years that I even gave names to just because it's kind of playful and fun. And we just need to kind of practice this a little bit. And then, yeah, we'd ultimately like the project is where you make your own up and then you try to get a line to slide along, like a tangent line to even slide along it. So you're finding every one of them, and we'll talk about that. Because that's Thursday's problem, if I remember right. So tomorrow's just more practice with this. I really do not have anything new to teach you. There's nothing else for me to explain here. It's not like I'm saving something harder for tomorrow. No, you're done. You know it right now. You just gotta like own it and get it to where you say, yeah, okay, I get how this works. So stay after if you like. Otherwise, I would recommend going and playing with this stuff in your assignment right now. And then ask me questions at the start of class tomorrow. That'd be a great, I could actually talk the whole time tomorrow just answering questions you ask if you have those questions. Or I have all kinds of stuff I can make up too, so.
I kind of have a question, like a comment first. When you were like describing like why 8x squared or whatever was like done by chain rule, that was like super helpful with like the chain rule and seeing why it was super close to the product rule. And then relating that to why we're taking the derivative in respect to x and why we would write y prime, it was just super helpful. But I was wondering if there was like spots in this class where finding the derivative in respect to y would be more helpful. I can't see it, but I was just wondering.
Yeah, with respect to just x and y and a graph that's x and y, we'll never do it. You'll never need to do that. And the only reason is because the only reason you would do it is to redefine slope as run over rise. I mean, you're used to saying, hey, look, that's a big slope. Look how steep it is. That's a big number. And that's a small slope. That's a small number. And that's because you define slope as rise over run. And by the way, if you redefine this as run, which is really small, over rise, which is really large, you'd get a small number for that slope. And that's why people do it that way, because it would seem backwards to give that a slope of like 2, and then this is a slope of like 10. You know,
Okay.
I want a big slope to have a big number, and that's why we picked it, but it's totally random, like which one should be on top. Why is it rise over run and not run over rise? Again, I bet nobody's ever talked to you about that. Like there's reasons for things. And so we'd like this to be a big number. And so if you call it rise over run, because it is really a ratio, it's a ratio of how far I go horizontally and how far I go vertically, and you could list it any way you wanted to. You actually wouldn't even have to write it as a fraction. You could just write rise equals number, run equals number, and never even make a fraction, just make a list. It's like a number that takes 2 numbers to describe it. So for that reason, because we're used to saying slope is rise over run, we're always going to say dy over dx. However, if you take further classes later on, there's things called partial derivatives that really get at what I was talking about in the gardening. Like I'd like to find out how the tomatoes growing with respect to water. So I'm going to change the water and leave the other ones constant. I'm going to treat the other letters like light as a constant. So I'll take the derivative of light and call it 0, because I'm not going to change that. I'm only going to change the fertilizer. And so you can conceptually, if you conceptually understand calculus, you can take the derivative with respect to any letter you want. We just aren't going to need to do it with what we're doing right now. So that's a terrific question.
Okay, that makes sense.
I had a question. I was looking at my notes from when we were wrapping up that very first problem that we did, where we ended up with the 2y squared minus 6 minus 4y plus 6 over 4x minus 6y minus 4xy. Because yeah, the blue one. Keep going. Further down. Yeah. In the box there.
Yep.
So I'm wondering, the term at the end doesn't have an x or a y on it. Where did that go? Because I see.
Yeah, I was actually just looking at this and seeing there's a -6 and a +6, and it's like, what the heck's going on? I think that 6 is the 6x, and I think it's supposed to have x.
Okay.
I think I blew it. Is that true? I'm going to stare at this a minute. Yeah, it is.
Okay, yeah, because that was.
Again, that falls into the category of a stupid mistake, right? You got a lot going on here. Like even to write the dumb thing down correctly is no joke. I'm not excusing myself. I'm actually helping you excuse yourself and recognize that.
Yeah, that was weird, because I saw the -6 and a +6, and I wondered like why we didn't just cancel those out, or if I lost an x along the way. So that clears it up.
Yeah, sorry about that. And I'm going fast enough that it's hard for you to process enough to, but don't be afraid in class to speak out. It's like, isn't there supposed to be an X there? And if the answer is no, then good. I just gave everybody time to process a little bit, made me slow down, right? So it's like, oh no, let's go back and look at it. Oh no, that's supposed to just be a 6. So don't feel like you have to be right before you say something. Because obviously maybe you saw that at the time, maybe other people did too, but you're just learning this, and so you feel like the room is this many people, how come nobody said anything about that? Because that wasn't like I wasn't doing calculus there, I was just like copying. I was copying down. Like that's a really, really dumb mistake, right?
I definitely did not see that, but I will see you guys later.
See, Arnie? Yeah, I didn't either. That's why it's kind of cool to check your work. I mean, if you have a way to kind of check it, like I would have at least known, hey, the slope didn't work right.
Okay. I'll see you
Actually,
tomorrow.
One really quick point. We did check this one. Did you notice that?
Oh yeah, I think we did have.
So how
We
come-
ended up with an 8 or something.
No, it worked. Like this is the one where we got a slope of 0, remember?
Yeah.
How come it didn't catch that mistake? Well, notice what X was. X was 1, and so
Oh, so I guess
turns
that's like
out
really
that we got
lucky.
incredibly lucky, if you will, to not catch that mistake. If X had been something other than 1, it wouldn't have worked, and then we would have. Then I would have stared at this for 6 hours trying to figure out what I did wrong.
Okay.
Interesting. Good question. All right.
Yeah, see you tomorrow.
See you tomorrow.